Right, so let's take a look at the next parameter here. So this one is the sort of the at the money liquidity, I guess, model or function. So in here, let's use a bit of colors just to make sure we understand. Right here, if you can follow my pen, in black, you have the mid, okay? And then around that, so this is the mid here in black. If I put it in black, it's going to be actually more intuitive. So right here, you have the mid. Mid. And in red here, you have, and in red here, you have the ask price, and you have the bid price, okay? And in dotted lines here and here, you have how these two red lines change as a function of this guy, okay? So this is essentially saying that forget about that P for now and assume that alpha is just a constant. So if alpha was to increase, you would have an increase in here and a decrease in here, okay? But however, because it's a function, and it's a function of the position size, you want to be able to make sure that if the position is bigger, then instead of coming here, you go there, and you come here, okay? So one way of doing this is through the equation I mentioned before. So you would say that alpha p is equal to alpha 0. So alpha 0 is like for the smallest possible infinitesimal unit of options that you want to buy. So it would be a minus alpha 0, 1 minus exponential of minus eta alpha p. Okay, so imagine eta is just a positive number for now. What this is saying is that when the position here, this position is really, really big, then this becomes really small, and essentially you have at the end alpha 0 plus a minus alpha 0, and you have a. Okay, so that means that this guy has come all the way down here. Okay, right? So this is for the I guess this is for the at the money bid ask spread. So an eta can be seen as some sort of, so let's pick a color here as well. So that eta here is known as the elasticity sort of equation. So the smaller this is, the more elastic is the option that you're trying to buy. So for example, if you're buying an option on a big macro index like the S&P, it's going to be much more liquid than something like a very obscure kind of equity. So for a very obscure kind of equity, the elasticity will be much, the value of eta will be much bigger and the elasticity would be much smaller. In terms of making it more intuitive, I should have perhaps put 1 over eta to make it a little bit more intuitive, but given that the paper was published in this form, I am presenting it in that form as well. Okay? So the psi parameter here is also controlling the bid-ask curvature. So that essentially is saying that the further away you get from the at the money, the less liquid your option should become. So you have to come up with this very simple change of variable to allow you to address that specific bid-ask layer. Okay? All right. So in terms of calibration, one very easy way to apply the optimization rule is to try to solve the distance squared between a pointwise implied vol and the points induced by the parameters of your IVP model. So note here that the error squared has been done on the implied vol itself. I, however, recommend you to do that sort of optimization process on the price space instead, because especially as you get to shorter tenors, the vega is so small that when you apply these fetching algorithms that we've discussed before, you know, the Brent or the Newton-Raphson or the bisection method, the implied vol values that you get for short tenors is such that there's quite a lot of volatility that occurs here, because again, in the price space, volatility for these short tenors is so insignificant that you can have quite a lot of drastic moves in implied vol in that region that you don't necessarily want. So it's best to do it on the price space instead. Okay? All right, so I'm not going to dwell too much into that slide here, but essentially this slide is saying that you can also find in closed form the values of these parameters, but that requires quite a lot of arithmetic, which I'm personally terrible at. But if you're good at that kind of stuff, you can try to do that exercise yourself by just selecting few specific points of the implied vol and trying to solve that system of equations. All right, so now let's talk about statistical arbitrage and risk management. So usually these two fields, they don't talk too much to each other, or not enough in my opinion. Especially in risk management, most of the risk systems are very symmetric in the way they see the price going. So whether the price of or if the implied volatility value is very, very high, the move on the upside and the downside is always the same in risk management. And I feel that this is a bit of an, I guess, obsolete way of taking a look at risk, especially for implied vol. And I thought it would be a good idea to build a section where we discuss statistical arbitrage and risk management together, as we will see next. It's going to become a little bit more intuitive as we progress in the presentation. So first of all, the formula. So you have this formula here, which is what I call some sort of conditional bumping formula, or some sort of trading signal formula, depending on whether you work in risk management or in statistical arbitrage. I think the best way to take a look at what this can achieve for you, we can go through a very simple example. So here's the example. Imagine you are an options trader and you're in equities. All right, so we've seen that in equities, so you have variance here and you have log moneyness here. Okay. Your current implied vol maybe looks at something like this. It's really exaggerated, but for the sake of making sure we understand each other. But you feel that on average, your implied vol looks more like something like that. Sorry, it's really difficult to do straight lines here. Okay, so, all right. And you feel like you could be taking a position in which you buy this point of the implied vol and bet that the implied vol will go this way, and you sell this point to go this way. So you're sort of vega, you're sort of at the money vol hedged, because whether you take this position or this position, if you have a move going this way of the general, like a volatility surface, or this way, it's not going to impact as much as a rotation around the axis. So this is what I call like a skew-like strategy. Okay, so how can you use the generalized bumping formula in order to define a trading signal? So you can say, well, that specific movement looks a lot like the move or the change in the rho parameter. So you can say, well, I'm going to define the dynamics of the skew to be something like this. So mu minus rho t dt plus sigma 1 minus rho t squared dwt. Okay, so what this, if you were to plot that specific function, that specific function would look like something perhaps like this. So if this is time, and if this is rho t, so as we have seen, rho t is bounded between +1 and -1. And maybe in equities, you know, the mu, sorry, let's take a red here. The mu here, so that line here is on average right here, okay? So you start plotting what rho is through time, and you get something like this. So it's a mean reverting stochastic process, and you want to make sure that in situations in which rho is significantly different from the mean, you take the positions and then the dynamic hedging sort of strategy, which allows you to capture that kind of movement right here. Okay? So this is essentially what that equation is doing for you. So the task then will involve finding these guys and taking the historical deviation from this mean, and then put today's skew right here, and then take the collection of possible scenarios based on these historical distributions to define your trading strategy or your risk distribution. Okay? Sorry. So let's go back here. All right, so this is what that specific trading equation can achieve for you. So let's discuss the parameters of this trading equation or risk management equation. So you have in here the speed of mean reversion. So if you're familiar with the Einstein-Uhlenbeck model or the cointillation model, you're familiar with this. You have the long-term mean. You have alpha, which is the positivity flag enforcer. You have beta, which is the boundary flag enforcer. And you have your historical errors from your model. And then you have what I call secondary parameters, which are more there to optimize a little bit the backtests. I personally don't like it, but I've seen a lot of traders and a lot of risk managers quite keen on things that allow you to, make the backtest a little bit more realistic. So these are different ways to take a look at the dynamical property of your signal. Okay, so that kind of generalized bumping methodology allows you to explore all the known diffusions or most of the useful diffusions in the financial industry. So you have proportional bumps here, or called log normal diffusion. You have the absolute bumps here, so quite good with rates, mean reverting bumps, and then a mixture of some of these things above. So a stochastic process which is bounded here between -1 and 1. It can achieve all of these different diffusions with that very simple formula. Okay? So the benefits is that it's versatile. So once you've put that kind of rule in your systems, your risk and trading system can talk to each other, and that works with most of the asset classes. Therefore it's deployable and robust. So it's leading. So that term here is more relevant to, I would say, risk management than statistical arbitrage, because by definition, you always use leading indicators for statistical arbitrage, but that also allows you in risk management to also have a view in the way you can see risk. So you can have a little bit of bias towards whether your risk factor is going to go up or down. So you still allow yourself to explore both sides of the risk, but you can sort of propagate more particles or more scenarios in areas in which you can also have a view. So for example, if interest rates are very, very low, then you can incorporate the view that, well, most probably interest rate will go up, but I'm not sure about this, so I'm still going to allow my risk engine to allow that stochastic process to go down. So, but I will create a diffusion which allows me to explore more on the upside than downside. Okay, so that raises the sort of the property that some of these diffusion are much more realistic with respect to the scenarios that you create. So I invite you to take a look at vols and interest rates for that specific point. And also in risk, when you create that kind of more realistic diffusions, the kind of arbitrage scenarios that you get are much less in number than if you were to use just traditional diffusions, which take a look on movements on the upside and downside without any bias. Okay? So these are different ways of applying that trading formula to the different parameters of the IVP model. This is what I was trying to explain earlier. So for example, if you were to apply that generalized bumping formula for the at the money, then when you are around the long-term mean, so you would get some sort of, so if you're around the long-term mean, these two things are equal to each other, so that part disappears. And you have a normal sort of diffusion. So in this case, it's a normal diffusion and not a log normal diffusion. But what happens is that when you are significantly different from the mean, so for example, in this situation, then the deterministic part of the stochastic differential equation can bias the movement on the upside here and here. Okay, in these two situations. So your distribution in green here is no longer symmetrical. But that doesn't mean that you cannot explore movements on the downside, even though you are significantly away from your long-term mean, which is above you. Same thing on the other side here, obviously. So a view on the downside. Okay? All right, so there's like two different arbitrage conditions that happen to be in the sort of in common with all the asset classes. So you have the butterfly arbitrage and you have the calendar spread arbitrage. So the butterfly is sometimes also known as the call spread arbitrage, or because a butterfly is essentially a spread of call spread. And that specific arbitrage, the calendar arbitrage, is also known as the falling variance arbitrage. Okay? So here are other interesting secondary arbitrage concepts. So this one is, so one of the questions that you can ask yourself is that, is there a clever inequality that allows you to map the parameters of your IVP model onto a non-arbitrage condition? Okay, so this is what was proposed on the SVI initially when it was published, but there's a great deal of misunderstanding around that specific inequality. This inequality is a necessary condition. Here is a necessary condition, but it's not a sufficient condition. And this is a counterexample of a situation in which this inequality is verified, but you can see here if you plot the density. So this is the density of your call. So the density and the butterfly arbitrage are essentially the same things in different axes, essentially. So in here, when your density is negative, that means you have a negative butterfly. Okay, it was worth spending one slide on this because I've seen a lot of comment around this in the literature. Recently, there has been some sort of interesting papers that have come out which try to address these kind of properties, but I'm waiting for them to be peer-reviewed before taking them further. Okay. So this is the falling variance formula. So it's the same thing as the calendar spread formula that we've discussed. And in FX, so I'm going to spend 1 or 2 slides on FX itself because it's an interesting asset class. So in FX, you can have all sorts of other kind of arbitrages. So you have, you know, especially in high frequency in the early stages, there was a great deal of arbitrages around the triangle concept. So if the exchange rate between these two things weren't the same as the exchange rate of this with this, then people would buy that and sell these two things. But this is done on the spot. And also there is a bit of, you can actually achieve an arbitrage as well. Another way to see this is that if you have your triangle and one side is significantly bigger than the other two sides, then you can make an arbitrage, and that's what that specific line means. You can also have arbitrages theoretically on the implied correlation as well. But I mean, these ones, you hear quite a lot of things like this, but it's actually quite difficult to take any kind of position that would allow you to access that kind of information. But in terms of risk management, if you are to, let's say, bump individually sigma 1 and sigma 2, then you shouldn't bump at the same time their correlation, because the change in the correlation is induced by the changes in the value themselves, especially when you take a look at a triangle representation of that kind of geometry. You can see more intuitively why this is the case. Okay. All right. The core of the presentation is over here, but there was like few other slides that I was asked to incorporate in the presentation. So about the importance of de-arbitraging, so I get quite a lot of that, especially in risk management. The question is, so in trading, this is quite important. You want to be able to detect arbitrages for obvious reasons. But in risk management, you know, is this a critical thing? So there's no general consensus right now in the market on whether or not the implied vols that you generate using historical data should be arbitrage-free or not. However, I feel the majority of people believe that it should be the case. You want to have coherent risk scenarios, and once you have bumped your implied volatility surface, you want to be able to find the closest arbitrage-free volatility surface for that specific scenario. Okay, so one way to adjust the objective function here is that if you remember, we had that optimization problem laid down earlier. Now you want to make sure that it is subject to no butterfly. So actually, this is no calendar spread here. No, sorry, no butterfly, or butterfly, and no calendar spread here. Okay, so one way to do this is to take a look, for example, in FX at different moneyinesses here, and or delta. This is in delta space. I'll mention a few words next on what that means. And these are the different tenors. Okay, so you want to make sure that all the critical moneyinesses for all the known tenors are arbitrage-free with respect to each other. Okay, and that doesn't mean that if you were to interpolate between these different arbitrage scenarios, you won't be able to find an arbitrage, unfortunately. But it's still, I think, the best thing we have right now in the financial literature around how to address the specific open problem in quantitative finance. Okay. So the optimization process, for those of you who don't understand what that means here, essentially you are changing your objective function, which was this, to also incorporate a huge penalization. So K here is the penalization scalar. So if you have a call spread, if you have a calendar spread or a butterfly that occurs here, sorry, this is a call spread. So again, a spread of call spread is the same thing as a butterfly. Okay, it's usually easier to actually use a call spread when you try to detect arbitrage than a butterfly. So if you have your call spread here and your calendar spread here, you want to make sure that whenever you detect one, you have a huge scalar here that comes and penalizes that function and return, therefore, the closest arbitrage-free scenario, or you get much closer to the arbitrage frontier by applying the objective function or the optimization process this way. Okay? All right, so this is really for practitioners. So what can you do if you're not very good in optimization? One simple hack, and I call this a hack, but this is really, this presentation has been done for practitioners. One way to address that specific question is to sort of visit the call prices and take a look at the different tenors. So in here you're visiting the calendar spread arbitrage, and here you're visiting the call spread arbitrage or the butterfly arbitrage. And whenever you have some sort of inequality which violates the arbitrage rule, then what you can do is then increment a little bit this one and decrement a little bit this one, decrease a little bit this one and increment a little bit this one if you want to do some sort of pointwise de-arbitragization. It's not great, but if your initial vol is close enough to the arbitrage frontier, many times this very simple hack works. Okay? But if you were to do that in a more rigorous way, you can fall into all sorts of like local minimas if your first volatility surface is a bit incoherent. But given that this is for the CQF, I thought I would also address a very simple hack to the methodology. Okay? And again, if you're in so FX is an interesting asset class because you work in delta space. So especially if you're in FX, using that kind of algorithm has its limitations. So if you were to move the delta space information here onto strike space, visually you get something like that. So when you actually go down the route here, you're no longer, actually, so on this side, on the butterfly side, that algorithm works, but on the calendar spread arbitrage, you're really comparing apples and oranges. So I would ask you to be really careful when you try to apply that kind of hacks with respect to the different asset classes. Make sure you always come back to the fundamentals and always try to first address the issue rigorously, then through hacks. Okay? And eventually you get a very nice implied volatility surface like this one. If you have any questions, you can send me an email. I'll be happy to address your questions. And thank you very much for watching this video.